Good evening, gentlemen. In this brief video, I want us to consider a principle that Dijkstra lays out in this paper, The Programming Task Considered as an Intellectual Challenge. This is EWD273. And this principle is something that also John Carmack tweeted about a while ago, but I don't see spoken about in many places. And it's a very, very deep and profound principle that is easier to say than to understand. It's easier, you hear it said, but you probably don't know what the real implications are for the software that you write. So Carmack says, when I started working in Python, I got lazy with single assignment and I need to nudge myself about it. And then here's the real principle. You should strive to never reassign or update a variable outside of true iterative calculations in loops. Having all the intermediate calculations still available is helpful in the debugger, and it avoids problems where you move a block of code and it silently uses the version of the variable that wasn't what it originally had. Now, the funny thing here is that the Carmack's justification is based on his view that we understand programs by debugging them, which is worlds apart from Dijkstra's views, which is you understand programs from the source and nothing else and never need to execute them to understand them. But what Carmack has gotten onto in this sentence here, never reassign or update a variable outside of true iterative calculations in loops, is a very, very, very profound principle for programming. And if you try it, and if you really try to live by it, you will find all sorts of marvelous things happening to your code. And in future videos, I hope to show by example the kinds of simplifications that it leads to. But first, I want us to talk about Dijkstra's justification for this and how he puts it. Because what Carmack says here is that it's useful for the debugger because you have the intermediate calculations. But this doesn't get to the heart of why you want to do this. So in this paper, perhaps we'll read it another time, but I want to just jump right over to, let's go to this section, and then we're gonna, let's just jump to the numbered section. Okay, so here we are. I'm going to just read the paragraph before and the first principle before we jump to number 2, but I guarantee you it's worth your while to understand what he's saying here in number 2. So we're going to leave a marker in the description for when I get to number 2 if you want to jump there, but I would advise you to take this introductory material also. Looking for intellectually manageable program structures, one is immediately faced with the question, but how do we manage complex structures intellectually? What mental aids do we have? What patterns of thought are efficient? What are the intrinsic limitations of the human mind that we had better respect? And this comes back to Dijkstra's idea about humility in programming. You want to be a humble programmer. You want to recognize that you can't understand this, that your limits are so near to what they're far much closer in than you want to believe if you're a programmer who's just self-infatuated and believes he can do anything. But if you approach programming as a humble programmer with Dijkstra, the first question you're asking is, how do I manage the complexity? Without knowledge and experience, such questions would be very hard to answer. But luckily enough, our culture harbors with a tradition of centuries an intellectual discipline whose main purpose it is to apply efficient structure into otherwise intellectually manageable complexity. This discipline is called mathematics. If we take the existence of the impressive body of mathematics as the experimental evidence for the opinion that for the human mind, the mathematical method is indeed the most effective way to come to grips with complexity, we have no choice any longer. We should reshape our field of programming in such a way that the methods of understanding become equally applicable, for there are no other means. And then I want to skip this section here. So the first principle here that Dijkstra puts down is what is colloquially the no-go-tos rule. But let's read it in context here because he says something a lot deeper than one may think. When programming, one should constantly bear in mind that although the program text is the last thing that leaves the programmer's hands, the true subject matter of his trade consists of the possible computations that may be evoked by his programs, the computations the making of which he delegates to the machine. When we say sloppily that a program is okay, we mean that the corresponding computations satisfy the requirements. That is, in other words, we should regard the programmer's activity not as producing programs, but rather as designing a large class of computations. The obligation to keep our intellectual grip on what may happen in time, while the static program text is the last thing we can lay our hands upon, the obligation to understand the computations as they evolve in time via the tangible program text yields an urgent plea to keep the sequencing rules, in other words, the mapping between the progress through the program text and the progress through the computation, as straightforward as possible. And this is what Carmack is benefiting from. He may not, great programmer, but he may not really appreciate what's happening here. The reason this principle works is because it's keeping the mapping between progress through the source, which is what he wants to look at while he's debugging his program, and progress through the computations at runtime, simple. The mapping is almost one-to-one. Which line am I on? I'm on this line. And therefore, line by line, one variable, line by line, he's able to see the evolution of the computations. As a result, I decided to abstain in sequential programming from the goto statement and to perform all sequencing control by conditional, alternative, and repetitive clauses and the subroutine mechanisms. And so that's the framing here, that's the context. But now we get to the meat of this video and what I really want to talk about. I would call this principle here, these principles here, I would call them normalization laws. If you think about in database programming, if you're familiar with EF-code and the idea of normalizing a database, so different things, but basically it's these are principles which EF-code introduced that explain how a relational database should appear, and the more normalized it is, the more it follows this normal form, the easier it is to use in practice and to update and to change and to reason about. So these are the same kinds of things. So we could say that Dijkstra's first normalization law is don't use goto at all. Just use what is colloquially called structured programming clauses. But now the one which I think is really profound. So here we are at the second principle. Another conclusion, especially related to sequencing. Let me explain this term sequencing. By sequencing, Dijkstra means how you go from individual program statements to compound statements like primarily the semicolon, but then there's various other things. If statements, gotos, just how does your program get tied together, and what's the sequence of computations that you're instructing the machine to use. So he uses this term. Another conclusion, especially related to sequencing, is the following. Whenever a construction is composed by means of a sequencing clause, encapsulate and find a description of its net effect in which the fact that it contains a clause is no longer transparent. If to write, if x is less than 0, then assign negative x to x. This means replace x by its absolute value, and the latter description is equally applicable to both cases. And if you have not a ready-made function, such as the absolute value, at your disposal, in terms of which to describe the net effect of such a compound statement, invent this function and be sure that its properties are nice and also the ones that you want. If you cannot find such a function, don't ignore that warning, for then you are on the verge of messing things up. To give you an analogy, when programming in machine code, you can appeal to the add instruction, but in doing so, it is immaterial for you whether the hardware invoked has a serial or a parallel adder. So what is Dijkstra saying? He's saying that you should never, when you're programming, if you're composing something, if you have a variable and you have, you're going to make a change to it. So let's look at this a bit practically. Okay, so I've thought up a very contrived example, and what I want to do here is we have a program that gives you the speed that an object is moving at, and we're going to use integers and large numbers, so there's no consideration of floats. We're going to have floating point, we're going to have rounding, so it's a very simplistic idea. So like, for example, if I pass into this program that I moved 10 units in 1 unit of time, then I want that to be a speed of 10. And at the same time, if I say negative 50 units in 2 units of time, I want that to be a speed of 25, because I'm not concerned with the direction that I'm moving in. So I'm just going to compile this program here, which is saved as hello.c. Maybe let's rename it and call it speed.c. So I'm going to just compile speed.c, call it speed, and then I'm going to run it. And I'm going to give it 50 and 10. And you'll notice that I've not implemented it yet. So we're just printing out the displacement and the time. And it's very obvious here, the speed is going to be the displacement divided by the time, but then we need the absolute value. So one may say something like int abs, meaning the actual the displacement, but the absolute displacement. And we may do something like by default it's this, but if abs is less than 0, then we're going to say then abs gets negative abs. Now note this, or we could say, let's not even use abs, let's say if disp is less than 0, then disp equals negative disp. But at this point, displacement really is like an absolute value, so I'm just going to call it abs over here. So let's say let's call this disp, and let's say disp abs. You get the idea. So at this point now, abs is the absolute value, and we can printf and we can say the speed turned out to be abs over the time. Of course, if you pass in 0, something will go wrong, but get the idea. Speed is 5 over here, and if I pass in negative 50, I get 5. Okay, now coming back over here to Dijkstra, he's saying that you should never do stuff like this. Now I know in C that this is again a contrived example, so in C maybe I should have done this example in Go to make it a bit more clear, but the point is, even though in C you could do something here, like you could say that the abs is going to be if disp is greater than 0, then disp, otherwise negative disp. Or you could make this greater than or equal to, doesn't really matter. You can put a ternary operator in here, and then this works, okay? But many people have critiqued the ternary operator, and so let's just suppose you don't have a ternary operator, because we're trying to just get at the nature of what Dijkstra is saying over here. He's saying that in a situation like this, it's a mistake to attempt to construct this absolute value in this kind of way. And you can also see that this violates what Carmack was saying over here. Never reassign or update a variable outside of true iterative calculations in loops. This is not an iterative calculation. So the only way we can get around implementing this, the only way we can get around doing this if condition that updates displacement here, is to make a function. So we make a function here and call this abs. Let me just call it absval, because there is a standard library function for that already, and it takes in an integer. And the implementation of this function is, as you would imagine, very simple. If c is greater than or equal to 0, we're going to return c, otherwise we're going to return negative c. Okay, so nothing really to see over here, but note that what happens is we can now just call this function here, absval, and up until this point, nothing obvious about what we've done is really clever. But note that now it's obvious that we don't need this variable, because we can just use it over here. So normalizing the code according to Dijkstra's rules made it more obvious that we didn't need a special variable for this. And so that leads to code that looks like this. And you get the idea over here. So what Dijkstra is saying is never be in a situation where you're doing some kind of intermediate update to a variable of this form. It always leads to more complexity in the code. And this, when I first heard this rule, it sounded fairly extreme to me. I was like, okay, wow, that's an interesting extreme position. But I cannot emphasize enough how life-changing following this rule is. If you try and follow it, just try and follow it even for 1 month or for 2 weeks of your life. You will be astonished at how much simpler your code becomes. It's like magic. Because what happens is, at all sorts of places, you'll find that you're doing these kinds of intermediate computations. And when you're forced to pull them out and to make them into specialized functions, you end up thinking about the structure of your program in such profound ways that you won't believe it. So I would just heartily commend to you this methodology. I believe it is one of the most important principles in programming, and it enables you to get over so much complexity, and it's just amazing. So try it out.